let's make it happen. I think I could make this slightly bigger. There we go. We're going to learn about averages because we don't know enough apparently. So there's a lot of cool things in this chapter, a bunch of important topics. It's chapter 14. Please read chapter 14. But yeah, let's study the average and then go further. All right, so we know what the average is. Another word for it, the fancy statistical word, is mean. And if you think about it, it's kind of interesting. The average of a bunch of numbers has some cool properties that maybe we didn't consider before. So like here, let's say that we've got a data set. We got 4 numbers. A data set of 4 numbers: 2, 3, 3, and 9. It's like here's our data set on a number line just for fun. We got all the way. We got 2, we got 3, 4, 5, 6, 7, 8, and 9. What is our data set? 2. We got a 2. We got 2 3s. It's like this is almost a histogram. And then a 9 way over here. All right. And the average is 4.25 apparently. 2 plus 3 plus 3 plus 9 over 4 is 4.25 somehow. And that is a number right here, right? Right there. And so we all of a sudden notice that the average, I guess, maybe I can put that not in green, but in like rainbow. Here's our average. It's not a number that was part of the original data set, was it? So the average doesn't have to be one of your values. That's one interesting fact, right? The average doesn't have to be a whole number. If your data was whole numbers, it's totally fine. It's 4.25, right? That's kind of weird, right? It is somewhere between the smallest value and the largest value. It's kind of like pulled to one side, of course. But it doesn't have to be halfway in between at all, does it? So that's all kind of very interesting. The average is kind of the balance point. If you put a bunch of weights, that's kind of what it's saying. The average of your data set is right there. If you put weights in those spots, if your number line was actually a real thing, you put weights in those positions, it would balance right there. So that's what an average is. And it's in the same units as the data. So if these were in inches, your average is 4.25 inches still. So that's still a thing. Okay, so yeah, we do know another kind of statistic that is a value. It's forced to be a value in the collection. The opposite almost, or something very similar to the average, is the median, right? So the median of these numbers is, well, the middle, there's 2 middles, but you take the average, it works out to still be 3 in this case. So the median of these numbers is 3, and that is a whole number still, and that is a value in the collection still. So the median and the average are slightly different, aren't they? So that's kind of weird. So yeah, I have a question for you to ponder. There's not a ton of us in this room, so maybe just think about it yourself. It's hard to have participation when there's only 2 people here. But here's 2 histograms. Think about them. Just think about them for a second. You don't have to write your answer down anywhere, but just ponder this question, please. Data set A, data set B, the histograms. So really the only difference is like these values got moved over to here kind of for this one. Think about the medians of these data sets and think about the means of these data sets. Are the medians the same or different? And are the means the same or different? So just think about that for a second. And then we can talk about it. It's like, what do you think? Let's see here. Like, how is this data set built? You can think of this as like, I don't know, there were 2 1s, 4 2s, 6 3s, 4 4s, and 2 5s. Like, maybe there are a couple 5s right here. And then those 5s got moved to be a couple 10s over here, maybe. And so if you think about the median, right, it's just the middle value. It's the one that's smack dab in the middle. It didn't matter that this got moved over to here because it had nothing to do with the middle anymore, right? It was already past the middle. So the middle is still this number, which apparently is 3 right here. And it's the same here, isn't it? Just the 5s got swapped out for 10s. See how that won't change the median? That won't change the median at all. The medians will be the same. So the average is telling us potentially something different, right? So the means, though, if it's the balance point, it was balancing here before, But now it's balancing somewhere over here probably now, right? So the balance point is for sure changed. Yeah, the balance point is for sure changed. It's probably, I don't know, something like that or something. I can't guess it very easily, but you can imagine it's probably right there. And so which is the bigger one? That's the one where the tens are where these values got moved over, right? They're going to be different. They're going to be different, and the bigger one, the bigger mean, is the one with the bigger data. Yeah? Does that idea make sense to us? Is that what we're thinking about in our minds? So the median and the mean, both important. They're telling us something about the center of the data, but it's kind of two different ways of approaching it, right? Two different ways of approaching it. And it's depends on your use case, which one you care about. So let's compare and contrast, right? So the mean is your balance point again. It's like the center of gravity. If you had weights on it, if your histogram was just a bunch of weights, it's where it's going to balance. Yeah, so I went and drew the balance points already. We're good. Awesome. And then the median is just like 50th percentile. It's the thing, it's the middle of that data set. It's the actual element of the data set, usually, unless there's an even number of things. And it's just like right where the center lies. So here's this picture, very pixelated, but I hope you can kind of see like the median is the middle value. It's where like there's 50% to the left, 50% to the right. And then the mean is not necessarily the same as the median. Sometimes it is, right? If the mean was right about here before, but the median, the median was right about there, but the mean was kind of tugged over because you had a bunch of big values. It was kind of pushed over a little bit because it's going to need to balance with those heavier things, right? It's going to need to move that way. So that's kind of the difference, okay? And sometimes, though, the mean and the median are the same. They are sometimes the same, and that's when your distribution, when your histogram is perfectly symmetric, right? If it's perfectly symmetric, it looks something like this. It doesn't have to look exactly like this, but this is a picture we're going to have ingrained in our minds today. You can see that 50th percentile is right there, and also it's going to balance right there. So the mean and the median will be the same if your data set looks like that, if it's symmetric about some center point, okay? If you've got some skewing going on, and that's this, like you've kind of tugged over the values in some direction. You've made some bigger. It's not symmetric anymore. If you've skewed your data set, or if it just happens to be skewed, then the mean is pulled towards the way you pulled everything, right? It's pulled towards the direction of your skewage. Like you tug the values that way from something that looked symmetric, and so that means your mean's going to be tugged that way. All right. So the tail is going to go in the direction of that tail of all those values. It's a long little tail. Okay, so yeah, that's mean versus median. It sometimes is the same, but it doesn't have to be. All right. Any questions about that? So some things we maybe haven't thought about for means and median. All right. I will go to code in a second. Let's do one more slide, and we'll go to code. So let's see. We would like, right? You're a data scientist. You've got a bunch of data. You want to present that data. You want to tell your boss about it. So you'll it's hard to tell somebody what your data set looks like by just giving them a few values, especially the min and the max, right? So if you tell somebody, oh yeah, my data set is this, and here's the min and the max, that really doesn't say anything at all about what the data set looks like, right? You have a million different options. So like, I don't know, your data set could have looked like this. Boop. Pretend that these are all to scale and the same. Data set could have looked like that, kind of symmetric. Data set could have looked like that. Boop. The min and the max are the same, yeah? See that? The data set looks completely different. Could have looked like this. Whee. Min and max are the same. There's just a bunch more of the maxes, yeah? It could have looked like this, even. Could have been boop, boop. Yeah? So if you tell your boss, oh yeah, here's the min of the data, here's the max of the data, it doesn't mean anything, right? It doesn't really say too much. says something, but it doesn't say too much. If you give them the average, that does help a little bit, right? It'll be able to distinguish some of these guys, like that one versus like this one. This one will be totally pulled that way, right, for the average. This one might be a little bit to the left here. I have no idea. Something like that. And then this one would be in the middle again. So even the average, like when you give them the average, those two will end up being the same. So even the average doesn't tell you everything. Median as well. If you start giving more statistics, right, then you get more. You get more knowledge. But yeah, that's kind of nice. So but that does give you a decent amount of data. That does give you a decent amount of data. Maybe you add in the median, but there's something more that we would like to have. And it would also be nice to know like how spread out is your data, right? How spread out is your data, because that tells you like how close together are they. Like say you had, I don't know, here's 0, here's 10. If your data set was this, like a 0 and a 10, your average is 5, but your values are way apart from each other. But if your data set was like 4 and 6, right, your average is still 5, but your values are very close to one another. So it would also be nice to know, like in general, how spread apart is my data. And mins and maxes will give that to you. That's still helpful. But it would be nice to have something else. All right, so let's just study in code for a second, just averages in general, and then we'll talk about how to like measure spread outness. So let's get all the people in like the San Francisco jobs, and let's go and get all of them where the salary values are above 10,000, because we know that there were a few zeros in that data set. Well, let's call that San Francisco. And let's do a histogram of that over the total compensation. This is just kind of something we did last time. Compensation, and the bins can be what we did last time. 10,000 to 700,000, going up by 25,000. Cool. So this was our data set, right? And the means versus the medians. Now let's try to imagine, like, where do you think the mean is? Where do you think the median is? Yeah. So let's see. I'll get sf.column total compensation. And let's call that something, because I'm going to use that a bunch of times. Compensation is that. And let's get the median. 50th percentile. I would say it's probably around where the spike is, right? A little over, like, almost 150,000, maybe 130,000-ish. There we go. Nice. So that's the median value. But do you see that, just like the picture from the other slide, there's a little bit of a skew to the right? It's being pinched away in the right, going to the right there. That's what's happening here too. So these large values are going to change where the balance point is. So I claim that the average will be more to the right because of those large salaries being tugged that way. All right. There's a bunch of different ways to ask for the average. You can be like compensation column dot mean, and it really is a little bit bigger. It's 138. But you could also do what, np.average of the compensation array. You could also do np.mean. There's also np.mean in addition to np.average. You have so many options. They're all going to give you the same value. But do you see how it got tugged over? Can you kind of see that from the histogram now? That average is getting pulled over to the right of the median because of these large values. You can see that tail going there. Yeah. And so it is useful, it's like, to be like, all right, the min value is this, the max value is this, the median was this, the average was this. Because if you compare the average to the median, you can be like, oh, okay, there must be a tail in that direction. There must be some larger values, like pulling it to the right in this case. And so even if you don't if you're not able to give somebody a picture, you can still tell them a lot with those numbers. Now let's come back to this idea of spread outness, because that's also important, right? You tell somebody the average was this, average was 5. They don't know if the values are way spread out, they weren't anything like each other, or they were really close, and they were kind of similar. So you'd still get the same average, and we should have a number then. Like how spread out is the data? In addition to having the min and the max, that's not enough. What's a value that can tell us how spread out that data is? And the number that people came up with is called the standard deviation. So maybe you've heard of that. We're going to study that in this chapter too. So the standard deviation, SD for short, it is going to measure how spread out the data is from the average. So we care about the average. That's why it's part of the average chapter. So the standard deviation is a measure of how spread out your data is away from its average. Okay? And so the way you calculate the standard deviation, it's a very disgusting calculation, but this is what it stands for. It's like you take the root mean square of deviations from the average. I'm going to explain exactly what that means. There's also a library function that does it all for you, but the way that you do it, the way that you calculate the standard deviation by hand is you remember this. It's the root mean square of deviations from the average, and you do it backwards. So like the very first thing you do is the average. You calculate deviations from the average. You square those deviations. You take the average of those squared deviations, and then you take the square root to bring it back to the same units. That is disgusting. We will talk about it though. Okay, so yeah. The nice thing about the standard deviation has some cool mathematical properties. No matter what your distribution looks like, any of those, for example, the standard deviation tells you something very cool and strong about your data set. It tells you that no matter what your distribution look like, pretty much all of your data are a few standard deviations away from whatever the average of that column happened to be of those numbers. Okay, so that kind of puts every data set in the same kind of range. Like all the values in your data set are like maybe 3 standard deviations that way, 3 standard deviations that way. That's as spread out as it usually is. All right, which is nice. So let's learn about standard deviation. Let's calculate it. Let's do the standard deviation of these numbers to start with, and we'll do encode. All right. So maybe you've studied standard deviation in like a statistics class before. We are going to study it again. And this is a very good number. It tells you how spread out your data is from the mean, from the average. So, all right, here's my numbers. These guys. These are my nums. I'll say make array of exactly those numbers. And what is the average of these numbers? Well, we can ask Python. I'll call that mean. np.mean over those numbers. What is it? 4. Apparently the average is 4, which is not, it's a whole number, but it's not an element of our data set. Okay, so the way that you calculate standard deviation is the very first thing you do. It's the root mean square of deviations from the average. So you do it backwards. You read this backwards. The very first thing we do is we took the average already. It's 4. And then the next thing we do is for each of these numbers, we calculate how far off they are from the average. How much did they deviate from the average? All right. So the deviation, it's you take your numbers and you subtract the mean from them. And so this is saying for each number, how far away are they from the mean? The first number, 0, is -4 away from the mean. Does that make sense? The next number, 1, is -3 away from the mean. That's how much you'd have to starting from the mean, how far away you would have to go from it to get to that number. The 2 is -2 away starting from the mean. Yeah? So that's what that is. These are called the deviations from the mean. Deviations are those. And so that's saying how far away is every number in our data set from the mean value. Okay? And yeah, let's maybe turn these into a table. I'll call this, make a table with some columns so that you can see this in full. I'll make like our original values, those are our nums, and then our deviations from the average. Deviation from average, that's our deviations array. And I'll call this table calculation steps so that I can add to it, because we still have more steps to go. We're just learning to do it manually. Of course, there's a there's a function for this, but we'll get to that later. So, all right, for every value in our data set, here they are, and here are their deviations from the average. What would we have to do starting from the average to get to all these values? To get to 9 from the average, you added 5. To get from 0 from the average, you add -4. So those are the distances from the average, right? So we need to next take their square, because essentially we want the average deviation. But we can't do that with the current, because of the negatives and the positives. The idea of the average, it's the middle, right? The average is the middle of this data. And so these deviations from the average, if they're all wrapping around the middle point, the sum of them, I hope you can see, is 0. It's like there's just as many below as there were above, because the average is the middle. That's what it means that's what the deviations mean. And so if we were to take the average deviation, of course, if the sum is 0, the average deviation is 0. And that's not telling us much. So what we need is a way to interpret these deviations as a distance, and we kind of need to get rid of the negatives in that case, right? So because then we could do like the average distance away from the mean, and that would tell us the spread outness. Yeah. So we have two options. We have two options to get rid of those negatives. The standard mathematical options are, we could take the absolute value of all those deviations, because then we'd have positive numbers always, and we'd never have to worry, and we'd have like an actual number when we take the average and the sum of those deviations. Or you could square them. We could also square them. It's another normal math thing to do. And just for math reasons, they chose to square them to calculate the standard deviation. That has better mathematical properties than the absolute value. Like if you've taken a calculus class, you can understand, I'm sure. You can take a derivative if you square things. So that's why we're going to square those deviations, because right now the negatives are canceling out the positives. And we want to know how spread out things are, so make those negatives positive too. And we'll do that by squaring the deviations. And so that's deviations squared. I hope I spelled that right. So squared deviations. So now here are all the values. Now it's 16, 9, and 4, and these are all positive, and that's how spread out things are. All right. So let's do calculation steps with the column squared deviations from average. Those are my squared deviations. So now here's the steps, right? Start with the original values, get their deviation from the mean, and then square those deviations. So now everything's positive. And then the last few steps are, you take the average of those squared deviations, so mean is root mean square of deviations from average, and you do it backwards. You take the average of those squared deviations, np dot mean or np dot average of the squared deviations, and that's telling you how spread out those things are, right? This is a number, 7.777 on forever, and this number, if the original values were in like inches or something, our units that we're working on right now, after we square something, like they're in inches squared, so they're not in the same units right now. So this value that we just calculated, the mean of the squared deviations, it's units, original units squared right now, and this number has significance. It's called the variance. That's a number that people care about in math still, but the units are wrong right now. So it's called the variance. It's 7.77. If we want to get back to the original, like how many inches apart, not inches squared apart are all these values on average, we're going to take the square root, because we were in units, we were in like inches squared, go back to inches by taking the square root. All right. We square just so that we can get rid of the negatives. And so that is, so if you take the variance, then take the square root of that. That is our standard deviation, or SD for short. So the standard deviation of our original numbers is like 2.79-ish, okay? 2.79-ish, and that's the steps. All right, does that make enough sense? You remember that? Standard deviations, root mean square of deviations from the average. Are there any questions about those steps? There is a function that does it all for us, but I want you to understand where we came from. You see all the steps together? And so this is saying your data set, starting from the average of 4, is at most a few standard deviations away, at most a few of these numbers away from 4, right? So the smallest value was 0, that's just a few, like less than 2 multiples of the standard deviation away, right? The minimum value is less than 2 standard deviations away from the mean, and the largest value was 9, starting from 4. It was again less than 2 standard deviations to get to that 9. So all the numbers in the entire data set, no matter what your data set is, they're just a few standard deviations away from the mean. That puts everybody on an even playing field. It's very nice. Okay? So yeah, it's np.std, standard deviation, and then you just give it the original data set, and it'll do it all for you, but now you know how it did it. Okay? So that is the answer, and yeah, I think that's what I wanted to say. Let's see here. Yeah, so I want you to try now. All right, so let me give you all this code if you want to go to the code from class. So you have everything that I've done so far. And I have a question for you to try. So please take a few minutes to try this. You don't have to enter in your answer anyway, but I want you to think about it and try it. Try to calculate the standard deviation of these numbers, 1, 2, 4, and 42. That's your data set. Put that in an array just like I did. You should have my chapter 14 slides now. Put that into an array and calculate the hard way and the easy way. The standard deviation of the numbers. What's it going to be? You try to prove to yourself, like, oh yeah, this value that I'm getting back, starting from the average, every value in this data set is just a few standard deviations away from that, away from the number. It's how spread out the data is. So our standard deviation for this data set is probably going to be bigger because it's between 1 and 42 rather than 0 and 9. 1 and 9. Let me know if you have any questions. I'll give you a head start. Cool. Cool. All right, let's take a look. Let's try it. Let me do it quickly. So, okay. You can always check your answer with NumPy standard deviation, the standard deviation function. So now my nums are 1, 2, 4, and 42. So what's the average? That's the mean is np.mean over the nums. Probably useful to print that out. So the average is 12.25, and the standard deviation is np.mean. Well, here, let's just do it really quickly in one line. So the standard deviation, if we're doing it manually, it's like, all right, the very first thing we do, it's the root mean square of deviations from the average. So we got the average. It's called mean. The deviations from the average is take your numbers, subtract the mean from all of them. That's the distance away. So it's the root mean square of deviations from the average. The next step is square those deviations, right? Get rid of the negatives by squaring the deviations, squared. And then you take the average of those squared deviations, so it's NP dot mean of all those. And then you take the square root to bring it back to the original units. So to the 0.5 after doing all of that. So in one line is that. And you can check and see. Nums. Yes, that was doing it right. Cool. So are there any questions about that? Did you get it too? It is a weird thing to remember, but that's the way to think about it. And every number in your data set is just a few standard deviations away from the mean. This standard deviation is larger than our previous data set because the numbers they were spread out more than the other data set. I hope you see that. But it's bringing everybody to the same playing field because that last value, that 42, the question is how far away was 42 from the mean? Well, it was 29.75 away from the mean, but in terms of how many standard deviations, divide that by the standard deviation. 42 is just 1.73 standard deviations away from the mean, and that's going to be true of a lot of the data sets. All right, that's how you can think about that. So really the number 42, you can think about it in terms of those units, like how far away from it, how many standard deviations were each of these values away from the mean. So 42 was 1.73 standard deviations above the mean. That's kind of neat. The other one, our data set was 0 through 9. That 9 was about, I don't know, a little under 2 standard deviations because the standard deviation was 2.7-ish. That 9 was about 1.75-ish probably standard deviations away from above the original mean of 4. And so even though these data sets look different, that standard deviation distance is about the same. That's kind of neat. That's pretty cool. And that's called those are called standard units, by the way. So did I want to write anything? No. So standard units are a way to change the units of your data set in terms of how many standard deviations away are all these values. It's also called a z-score. I don't remember why they call it z-score. I think they just needed a letter that they hadn't used in the literature yet. But to get the z-score for any value of your data set, you take the value, you subtract it from the average, because that's the deviation, right? You get the deviation of that value away from the mean. So that's how far away that value was from the mean, and then you divide by the standard deviation, and then your result is how many standard deviations away from the average was this value. Okay. You get a negative value, that means your value was below the average. If you get a positive z value, it means your value was above the average. If you get a 0 z value, that means your value is exactly equal to the average. And a nice thing about when your values are in standard units, what happens? What does it turn your data set into? Say this was your histogram. We're going to get this image burned into our minds. If you turn all your values into standard units, then what is the average in standard units? It's always 0, right? Your average, because average minus average is 0. And then your standard deviation is exactly 1, because that's what we're defining it to be. It's here's a value 1 standard deviation away from the mean, 2 standard deviations away from the mean, -1 standard deviations away from the mean, -2 standard deviations away from the mean. So you can start thinking about your data set in those terms. Okay, so let's see. How do I want to deal with this? Yeah, let's look at this in code for a second. Let me try to explain what I mean by that, because it is a useful value. Right? Getting into standard units, that's just turning all the values into how many standard deviations were those values away from their means. That's getting everybody on an even playing field. Standard units. Let's do this in terms of an older data set. Let's do the sun's heights data set. These are the heights of the parents and then the heights of their son in inches. It's a father of that height and a mother of that height had a son of that height when the sun was done growing. And let's change these units into standard deviations, into standard units. Okay, so let's get the sun's heights. That's heights, column number 0, 1, 2, right? So this is all the sun's heights values. And we can get their average, right? Mean height is take the average of that column. So the average sun height in this data set was a little over 70 inches. And then we get the standard deviation of all those sun's heights. Let's just change all this to standard deviation height. It's np.standard deviation. Standard deviation of all the heights for the suns are about, looks like this, how spread apart are these values. It looks like the standard deviation of the heights is about 2.5 inches. And now what we can do is we can change the units of those sun's heights into standard units. How far away are all these values away from their original mean? So let's select out the sun column. So here's the sun's heights again. If we sort that, sort on the one and only column now, here are all the heights of the suns. Like the smallest height was 63. What was that in terms of standard deviations away from the mean? So if the mean was 70-ish, mean height, right? 63, what was its deviation, right? That's the smallest sun in this data set. 63 minus mean height, it was that many units away from the mean. That was its deviation. But what was its, what was it in standard units? How far away was it in terms of how many standard units? How many chunks of a standard deviation was it? It was almost about -3. All right. So the smallest value in this data set, it was about -3 standard deviations away from the mean. And that's going to be true of pretty much every data set. That's probably usually as far as it gets. That's what the standard deviation tells you. This was about 3 standard deviations below the mean. It's never going to get much farther than that. All right. And what was the tallest sun in this data set? Let's do sort descending equals true. The tallest sun height was 79 inches. We can play the same game. How many standard deviations above the mean now was that 79 inches? Maybe 79. It was a little over 3. It's still about 3, right? Standard deviations above the mean this time. So that's what the standard deviation is all about. No matter what your data set is, once you calculate this value, pretty much every value in your data set is going to be between -3 and +3 standard deviations below and above the mean, below and above that average of your data set, no matter what the values were. If the values were more spread apart, then the standard deviation is going to be bigger because it's a measure of how spread apart things are. But in general, all of the values in your data set, no matter your data set, will be about 3 standard deviations away from the mean. Not too much more than that. That's really, really cool to think about. Okay? And so instead of looking at these values as like 63s and 64s and 79s and 78s, let's turn them into like -3-ish and +3-ish. Let's turn all these values into how surprising were they? How far away from the mean were they in terms of how many standard deviations? And that's called turning these numbers into z-scores, or turning the data set in, changing the units into standard units. Okay? So to turn this data set into standard units, you just want to do this for every value. You take the value, whatever it was, subtract the mean from it, and divide by the standard deviation. That turns an array into standard units. So let's make a function called standard units. You give it some numbers as an array. I'll say numbers array. And what do? Well, you take all those values in that numbers array, you subtract from the average of those numbers, np.mean numbers array. That's giving you all the deviations, right? And then you want to turn it into how many deviations, how many chunks of a standard deviation are all these values away from the mean. So you've got the distance from the mean right now, divide by the standard deviation. This is turning everybody into a z-score, everybody into standard units. So no matter what your numbers array was, this will calculate and turn it into standard units, that function right there. So yeah, let's do my heights table. And we'll do with a new column, we'll put the sun's data in standard units. Because now I can say standard units on that sun's column, heights dot column sun. No, I did something wrong. There we go. And, oh, sorry, I need to turn this in. Let's call that heights again. Well, actually, just let's make sure that that works first before I go changing things. So here, I've added this column. And so for all these values now, these were the original values. These are in z-scores. These are in terms of standard units. So this value, how surprising was it? It was about one standard deviation away from the mean. This next height of a sun was that many standard deviations above the mean. That one was a little, just tiny amounts above the mean. That one was pretty much the mean, this value. And that's what your data set looks like. This value is about one standard deviation below the mean. That was a shorter sun height. And pretty much all of your stuff for most data sets will for sure be between like -3 and +3 standard deviations. And honestly, for the vast majority of data sets, pretty much all of your values will be between -2 and +2 standard deviations. So let me try to prove that to you. Let's call this heights. Heights is that. Do I want to say that in code? Yeah, we'll talk about that in a second. Like that's my heights table now. Let's get every of these values within 2 standard deviations. So what are all the heights values where the sun in standard units column values are between -2 and +2, right? Because that would be between -2 standard deviations below and above the mean. Those are all the values that are within that range, and these are just like, that'll give me back a table. All the values for the sun's heights that are within 2 standard deviations. That's that. And I can say, how many of those were there within 2 standard deviations? How many of those people, num rows, over the original heights table, dot num rows? So about 94% of the data was within 2 standard deviations of the mean. You see that? Only the largest and the tallest and the smallest suns were outside of that, because we did see about three standard deviations for the most extreme values in either direction. So all the values that are within 2 standard deviations is pretty much 94% of the data in this data set. Within 3 standard deviations, between -3 and 3, that is virtually all of the data set, 99% of it. All the values, and this is going to be true for pretty much every single data set you'll ever encounter. All the values are between -3 standard deviations below the mean, +3 standard deviations above the mean, 99% of the data. That's crazy and interesting to think about. So yeah, let's turn this into a histogram that kind of looks like this now. Let's do a histogram of the sun's heights in standard units. And I'm tired of typing this out, so let me copy and paste it. Let's do 15 minutes. And here is the data set in terms of standard units. And I hope you can kind of see that this is useful. Like, here are the values. Here's the mean of the values, right? The mean of the values is there. And most of the values are pretty much around there. Like this is 1 standard deviation away. There's a good chunk of the data, a decent chunk of the data is within that much. You know that 95% of this data set was between -2 and +2 standard deviations away from the mean. And then virtually all of the data, 99%, was between -3 and +3 standard deviations from the mean. There was just a few, there's very tall children, I guess. They're a little above 3 in this data set, but still 99%. 99%. That's pretty cool. Are there any questions about that? That's a cool property of the standard deviation. It gives us a spread of the data, and these values, these ideas are true regardless of the data set that you're using. 99% of the data is going to be between -3 and +3 standard deviations away from its mean. If the numbers are more spread out, then your standard deviation is just going to be larger. Okay, so that's what that number means. It means how spread out. It's a way of measuring how spread out your data is. Okay, that's pretty cool. That's pretty nice. All right, so we can finally talk about these bell curves, because we've been saying it all along. We've seen it come up so often. most of the data, a lot of the data sets that you'll ever encounter, including the ones that you generate as a data scientist one day, your values are going to look like this. The histogram, there's going to be a mean, and your values are pretty much going to be centered around that mean, and it's going to be symmetric, and it's going to kind of taper off. It's going to be this bell curve shaped thing because it's supposed to look like a bell. Okay, I guess here's your bell, and like there's the little thing that you ding inside of it. If you have a histogram, if your data set is bell shaped like this, then what that means for you is the average is for sure at the center. We already know that, right? Your balance point's right at the middle there. Your average is going to be at the dead center. And it also it does tell you something important about your standard deviations, which is nice. Right where the inflection point of these sides of this bell shape. And what that means is where it stops, where it like, instead of flaring this way, it starts to go that way. You see how it's kind of like this part of the curve is going that way and this part of the curve is kind of going that way now. That's what that means. That's the inflection point. So this is right there. There's your inflection point. And the same idea over here, the other inflection point, like it went from going that way to kind of in this kind of direction to that kind of direction. Those are called your inflection points. And that is the standard deviation as well. That's where that is pretty much most of the time. So the standard deviation is the distance between the average, so here's the average, and one of those inflection points. So like that is one standard deviation for you, okay? Which is a nice way, if most data sets, they just end up looking like this for fun, just due to some cool features of math. A lot of data sets in the world will look like this, and you can kind of read off very quickly from the histogram, all right, here's what a standard deviation is. Here's where the mean is. So that's kind of nice. Let's see. And there is like this is so important, and people see this so often. There is like an ideal bell-shaped curve, and it's called the normal distributions. Like that, this is what everything looks like. It's supposed to be this. This is the normal way for a data set to exist. So it's called the normal distribution when your data set looks like this, and this is what's going to be true about it. So again, your midpoint is the average, of course. And the inflection points are a standard deviation away from the averages, like that far, that far. But it also kind of tells you about what's true for how much data is between what and what. If your data set looks like this, then between -1 and +1 standard deviations from the mean lies, and this is true, if it looks like this, pretty much exactly, there is 68% of the data here. That's just a mathematical thing. There's 68% of the data between -1 and +1 standard deviations away from the mean. There is 95% of the data between here and here, 95%, between -2 and +2 standard deviations from the mean. And -3 to +3, that's pretty much everybody. Like mathematically, if your data set looks exactly like this, there's a formula for it. There's 99.73% of the data right there between -3 and +3. And we calculated this one and this one for our sun's heights data sets. The heights of humans looks like this, the data set. So that's kind of neat. And we pretty much got those values. So our data set looked like that. That's pretty fun. So that's if your curve looks like this, if your histogram looks like this for your data, this will be true. This much of your data is between this many, like one standard deviation away from the mean, 68% of your data, 95% of your data is within 2 standard deviations from the mean, and pretty much all of it, 99.73% of your data is going to be between 3 standard deviations from the mean, plus or minus. So yeah, not all data sets look like this. You've seen data sets that look wonky, that look like weird stuff. This stuff is true only for the normal distribution when your data is normally distributed, you say. But no matter your data set, if it's not bell-shaped, you still have some guarantees. No matter what your distribution looks like, still most of your data is between just a few standard deviations from the mean. It's not pretty much all of it, though, so maybe there are some outside of the 3. If your data set looks like anything at all, no matter the distribution, just the mathematical properties of a standard deviation, they give you that pretty much 90% of your data no matter what, is going to be 3 standard deviations away from the mean in either direction. So that's all distributions. All right. So all distributions, this is what's true for how many standard deviations away from the mean you go. It's still telling you about the spread of your data. It's still giving you information about what's where. It's just not as like things are more spread out, kind of. That's what that means if it's not bell-shaped. But if it is a normal distribution and it's perfectly bell-shaped, then we have exactly these values. This is what's in 1 standard deviation away from the mean, 2 standard deviations, 3 plus or minus 3 standard deviations from the mean. Pretty much everything is about 3 standard deviations from the mean. If it's bell-shaped, maybe got to go up to 4 standard deviations if it's the other one. That's all. All right. That's kind of neat, though. So it's telling you that no matter your data set, no matter the shape of your histogram, it's still telling you something. Okay. So yeah, that's what that means. And you can think about like what's where in terms of area. If this is what your histogram looked like, if you zoomed out and you had like 1 million data points, you turn it into standard units. This is like when you're trying to count things, it's really you're taking the area under this curve from here to here. I'm taking calculus so you understand what's happening right now. It's like if you had this exact histogram, you took the area from -2 to +2, -2 standard units to +2 standard units, that's giving you the area under that curve, and you'll find 95% of the data there. Okay, that's what that means if you're going between plus or minus 2 standard deviations of a perfect normal distribution of a perfect bell curve. All right, and because a lot of data sets they look like this, like the sun's heights, there is a mathematical way to generate this, get these properties for like I want to know how much data is between -3 and 1.5 and +1.5 standard deviation. Like you can get whatever kind of area you want, and that's called using the cumulative distribution function for the normal curve. So this is a little disgusting, but here's what it means. There is a function. Let me show you how to get to it. It's the normal cumulative distribution function, CDF. So just in case you need some like mathematical optimal answers here, it's you have to go into, there's a new library, it's called SciPy. SciPy. You import the stats library out of that, and it's stats.normalcurve.norm.cdf, and you give it a value. All right, and this tells you something about the area under that curve. So let me try to say what that means. So this is what this function does that I'm showing to you, and it lets you calculate whatever you want, is you say the CDF of some number, it's going to calculate the area to the left of your z-score being that. So this picture is showing what's going to be calculated when you do CDF of 1. It's like, all right, so starting at 1, what is the area under the curve starting at 1 going leftwards to -infinity? What's the area under all of that part of the curve? That's what that's doing. Okay, it's giving you all of the area from -infinity to that value that you cared about. And that's what CDF of something gives to you. Okay, so that's CDF of 1, and you can get the other part because it adds up to 100%, right? It adds up to 100% or 1. If you wanted this bit, right here, this stuff that's not covered in, that would be 1 minus the CDF of 1. Does that make sense? Because it's going to add up to 100%. So that would give you the other part of that. So just that one function can calculate the area of anywhere. And so usually you don't want from -infinity to something. Usually you want like, all right, my data set is a normal curve. My data is normally distributed. I would really like to know the area under the curve, like how much of the data is between maybe -1, here's -1, 0, and 1, between like -1 and +1, even though we know the answer is going to be 68%. What you can do is you can do CDF of 1, and that will give you all of this, right? It'll give you this area. And you kind of want to exclude, because it'll give you all the way to -infinity, all the way over here. You just want to exclude all these bits, right? All that stuff. You want to get rid of it. And so the way that you can do that is you subtract away from here, right, on to -infinity. So what's that green bit? That's the CDF of -1. You see that? So if you wanted between just -1 and +1, you get from here, which is -infinity to here, That's everything. You want to exclude this area, so you subtract CDF of -1. That's negative infinity to there. So yeah, that's going to give you the area between -1 and +1 if you use this function. So that's why you just need that one function to get whatever you need. And so, yeah, when you call it, this is like the optimal answer for a perfectly normal distribution. This is going to give you the percent of values from -infinity to +1 when I call it like that. So if you wanted the opposite of that, you just subtract 1 because it always adds up to 1. It's like, what's this? 1 minus that, that's from 1 to infinity then. Right? That's the other half, 15-ish, 16%. This is the percentage of values from +1 to +infinity. And so if whatever you want then, between -1 and 1, you can make it happen. So like if I wanted between, I don't know, -1 and +1, you'd say stats.norm.cdf 1 minus CDF of -1. Stats.norm -1. Oh, oops, .cdf. And there's your 68%. Cool. Are there questions about that? Does that make sense? That's how that works. And so, like, all right, these are the optimal answers. So between 2 and -2, you get these. 95% of your data is there. Between 3 and -3, you got 99.73. And then there's a bunch of zeros, and that's why they cut it off there. Cool. So that is a way to calculate these optimal values. If your data set is perfectly normal, this is what you can expect to see. And that's just a function that's built in. Any questions about that? That's what the mean is all about. Giving you some cool ideas. So all of these ideas, they culminate in something pretty neat. It's called the central limit theorem. And let me try to explain it to you. So, all right. If you've got a big data set, your data set is huge. And usually we have big data sets because we're getting a lot of data as data scientists. So if you take your data set and you sum up a bunch of the values in it, or you average a bunch of the values there of a large random sample, because usually you're taking large random samples, and you draw it with replacement, no matter what you're doing, no matter what your data set originally looked like, if you're taking sums of data or averages of data, no matter what the original distribution looked like, it could have been the wonkiest thing ever, it could have been any of these. If you're taking sums or averages and calculating those based on your data, the distribution of that average or of that sum will be normal. It will turn normal. And that's why we study the normal distribution. That's insane and very cool. It's called the central limit theorem. When you have a bunch of data and you're taking averages, for example, no matter what that data originally looked like, here's the original data. If you're taking averages from it, those averages will become normal if you had enough of that data. That's insane and very, very exciting and cool. It means that all the things we studied about normal distributions, they matter, no matter what the original data set looked like, because usually you're taking averages a lot or summing up things. So if you're taking averages, for example, as well, the average will be the same. Will be the same as your original population's average. It'll get close, of course. That's what we normally do. And the standard deviation of when you take an average, it's your original population standard deviation over the square root of the sample size. Over the square root of the sample size. And those are just weird facts. And I want to show that to you. So this is called the central limit theorem. No matter what your original distribution looked like, it turns normal when you start taking averages or you start summing things up. And I cannot express enough in words how cool that is. That's a very, very powerful fact of statistics. So let's go to gambling, the reason statistics was invented again. So let's talk about rolling dice. So here, let me make an array of all the ways that you could roll a die. 1, 2, 3, 4, 5, or 6. What's fair? You get all these options, right? I'll call that one die table. So here are all the values on a die, right? You know that when you roll a die, you have equal, if it's fair, of course, you have equal options of each one. So die, give me histogram, bins, equal NP to A range. If I try to center it, go from 0.5, 6.6 by ones. Boop. This is the probability distribution of you rolling a die, right? They're equal. You get in a ones just as probable as you get in a 2 or 3 or 4 or 5. They're all equal. It's a uniform distribution, right? So to be precise, this is absolutely not bell-shaped right now, right? This is not at all bell-shaped. This has nothing to do with the normal distribution right now. These are uniformly distributed. They are not normally distributed, all right? But if I roll a bunch of dice and do something that involves summing or averages, something very, very powerful and cool is about to happen. So like if I roll 10 dice, sample 10, right? Here's me rolling 10 dice and their values. Let's say that I roll a bunch of dice and I take the average value that I get, okay? So let's make a function that can do that quickly for me. So like average value, average die value. For you, give me how many dice you want to roll, your sample size. You give me a sample size. How many dice do you want to roll? Let me take that many. So sample from the die table, that many things. That's me rolling that many dice, right? It's with replacement. There's my sample. And then I want to get the average of those values as sample.column 0. I want to return that. So this function makes sense to everybody. When I call it with something, it's just rolling like 10 dice in this example, and it's giving me the average value of those dice. Yeah? And it's different every time because you're rolling different dice. It's random. So it's kind of neat. Let's say, again, central limit theorem applies. No matter what your original distribution looks like, it looks like this for us, right? If I do a bunch of these, give me the average stuff, those averages, the distribution of them, will turn normal. It will turn bell-shaped. It's insane. So let's roll if the values are large enough. It's a large random sample. So as the numbers increase, it looks more and more like a bell curve. And I think I've shown this to you before. But now let's spell it out, right? So let's roll 1,000 dice 1,000 times. So I'm going to keep track of all those. These are a bunch of averages of like our 1,000 dice. So it's group averages. Rolling a group of dice. And let's do it 1,000 times. NP to A range 1,000 times. Please do the following. I would like you to roll 1,000 dice. I get their average. That's my average of the group of 1,000 dice that I just rolled. And I want to add that to my group averages. Set that back into group averages. So this is me rolling 1,000 dice 1,000 times, yeah? And getting the average value each time I roll 1,000 dice. So average together the value on 1,000 dice rolls. Keep track of that and do that 1,000 times. All right? So that happened. And let's make a histogram out of this with column. These are sample means, right? Took a bunch of samples, group averages. And let's do a histogram with 20 bins, let's say. So here is the original distribution, right, of the dice. It's a uniform distribution. But I rolled 1,000 dice, took the average. I did that process 1,000 times. Look at how it turned normal. Isn't that amazing? And you better believe that if I did this for larger amounts of dice and more times, it would look pretty much perfectly normal. That's so cool, and it's gonna be centered around like whatever the true value is. I think you can imagine it's 3.5, right? That's the expected value for an average when you roll dice. But you see that it can fluctuate because of randomness, and that is beautiful. It turned normal, even though it originally was a uniform distribution. The distribution of those averages turned normal, and so everything we learned about normal distributions applies here. All right. And all these things are kind of neat. So like the mean will approach the true population mean, which is supposed to be 3.5. And then we can see that here. And then the standard deviation, which is kind of neat, will approach the original population standard deviation over the sample size. What was the original standard deviation of like the dice, the values 1 through 6? What was that standard deviation? That was die. So if we go to the original dice table, just the values 1 through 6. What was the standard deviation of those original values? It was apparently 1.71. That's our original population standard deviation, which sometimes we don't know, right? But for dice, we know. So it's that. And like that's what it's supposed to be. And the standard deviation of these averages, these sample means, the standard deviation of these group averages, that is this standard deviation. It's like 0.05. This is our empirical standard deviation. I'm doing our simulations. But this value, this standard deviation, is approximately, it's supposed to be, it approaches as the values get large, as you get enough samples, the original population standard deviation over the square root of the sample size. And our sample size was 1,000. Yeah. So what was our population standard deviation? I stored it in that variable. Divide by the square root of 1,000, because that's how much, that was our sample size, 0.5. This is our theoretical. This is what it's supposed to approach if you do this enough times. 0.054. It checks out. So this is why we study the normal distribution, because a lot of things that we care about generating become normal even if they weren't at the beginning, because we're going to take averages a lot of the time, because we care about averages. That's pretty neat. Any questions about that? That's a very powerful fact. It's called the central limit theorem. It tells us this. And maybe we can play around with, if we change the sample size, we can watch everything still check out, but we can see that the values fluctuate. It'll still look normal, but it'll look a little bit more wonky. It looks more and more accurate the larger the sample you take. So maybe I can do this process for different things. So let's do sample mean statistics. Give me a sample size and give me how many repetitions you want to do something. And then I'll do everything I did up here. I'll take my group averages, and repetitions times, I will take an average, and I'll use this sample size that we cared about. And then, let's see, what do I want to calculate? Let's do that histogram again. And let's also print out the sample size and the standard deviation of those sample means that we were generating. So this is just doing this process again where I can control, in addition to the sample size, how many repetitions I do. So I'll do, say, what was the sample size, colon. And if you give multiple arguments to the print function, it'll print things out with spaces. Here's what the sample size was when I called this function. And then this is standard deviation of sample means. That's NP, standard deviation of our group averages. And this should be approximately equal to this. As things get large, it'll be pretty much exactly equal to this equation that we have here. So with that, let's say that I made a small sample size. So sample mean. Let's say that my sample size is just 10, but I'll do a lot of repetitions. So try to get some good data out of it. 10,000. The distribution is going to look a little weird because your sample size is small with 10, but the standard deviation is mostly accurate, right? It's gonna look pretty much like what it's supposed to be, which is off by like a factor of 10, right? This is what it was supposed to be for the other one, but you can see that it's pretty much that, off by a factor of 10, which is perfect. So even that is still accurate, but the histogram looks a lot less normal though. All right, but the standard deviation is still kind of stuck with how it's supposed to be. Our original, our original was 1,000, 1,000. So let's say we increase our sample size to 100. That looks pretty much very normal, right? I did a lot of repetitions as well. So that is making it look more and more normal. So 100, you see that the standard deviation gets smaller because you took a larger sample, right? You took a larger sample, which means that there's going to be less variation once you do that. It's harder to beat the system, right? It's easy to roll like 5 heads in a row if you try it long enough, but it's really, really hard to roll 50 heads in a row, right? And so 1,000, 10,000 times, this will also look very, very nicely normal. And let's calculate after we did this. These were like the empirical standard deviations. Let's calculate what they were supposed to be. Again, this looked very perfectly normal. So let's do the sizes that we did were, for sample size, it was 10, 100, and 1,000. 10, 100, and 1,000. And let's loop through those for size and sizes, let's say. Let's print out that size and a colon, and what was it supposed to be? What was the standard deviation supposed to be? The population standard deviation, which we saved, over whatever your sample size was, the square root of that. So here were the values they were supposed to be. So like theoretically, this one's supposed to be 0.54. Pretty much it was. Nice. So this is checking out, even though the data set, even though the histogram doesn't look very normal. That's okay. This one now is looking very nice and normal. Sample size 100, we saw about 0.17, 0.17-ish, not too far off. And for this one, 1,000, the closer you get, right, the larger your numbers are, the more it approximates what it was supposed to be. So 0.0546, 0.0540. Now the issue is in the thousandths place rather than the hundredths place. That's very neat. That's very neat and cool. And I think that is most of what I wanted to say. Are there any questions about the central limit theorem? So just normal distributions, they pop up even when your original data set is not normal. That's amazing. Very, very cool. And because of this formula, this is telling us something. If we want to be very confident about where our data lies, and we know the standard deviations of things, we can solve this equation for sample size, can't we? If we really want our values to be squished and not too far off, we want to control the spread of our data, we can solve this, and we knew a sample standard deviation or something, we could approximate this somehow. You could solve for what sample size you needed. That's kind of neat, all right? And so let me show you that. So if you wanted to choose a sample size, let's say, all right? So you wanted to, we were trying to predict the average of something, and we'd really like to make a 95% confidence interval because we love those now. We'd like the width of that to be less than 0.01. We'd really like that. We want to be that confident, the values can't be that far apart. So we really like to be able to say something like, oh yeah, the values with a 95% confidence, they're within this range because that's between 0.01 away, right? Less than that away. But this one, we don't want that. That's too far. That's too much of a spread. We don't like that. So we can control that. We can control that. Maybe these are percentage values, maybe something like that. Why can't I get that red to go away? Oh well. But we know some facts now because we're predicting an average. If we had a large enough sample size, the central limit theorem would take over and our distribution would be normal of those averages. And we know that a 95% confidence interval is plus or minus 2 standard deviations. That's another reason we care about 95% confidence intervals. That's why people like those. We know things now. That tells us something very nice, right? So we'd really like to control our values so that the mean plus or minus 2 standard deviations contains the distance of those is not too small, right? Or sorry, not too big. Not too big. And so we can solve this equation, right? We can solve this equation for what we need, for what we're trying to look for. So we'd really like, let's see, the distance, if you're trying to go plus or minus 2 standard deviations, how many total is that? That is, it's really 1, 2, 3, 4 standard deviations in width, right? We'd really like to solve this equation if you think about it. We would really like 4 times a standard deviation, the width of 4 standard deviations, to be less than 0.01. Like that's what we wanted. And we could use that plus this equation to solve for what our sample size needs to be in order to be able to make that kind of prediction with that much accuracy. It's very cool. So this is just math at this point, but I hope you can see, like, all right, what is the standard deviations then? What's that equal to? Well, according to this formula, if the central limit theorem takes over, the standard deviation is equal to this. The original population standard deviation over the square root of the sample size. Like, we can make that replacement. So we have this to solve now, right? If you move over things, you know that the square root of the sample size needs to be greater than or equal to whatever this is. But a lot of the time, like we were talking about in previous chapters, like, it's really hard to figure out the population anything, like let alone a standard deviation, like a population average for like everybody in the US. We can't go out and interview people, right? We can't do that. So we have to make a guess here. Like, what's the worst? What's the largest that value could be, maybe? Because that would give us like a worst case scenario. So that would be great. So if we don't know the population standard deviation, and we usually don't, we could maybe take a sample. We could get a sample standard deviation. We could try to play around with this because like we're trying to do all this before we even take a sample. Even maybe we don't even have a sample standard deviation. If we knew the worst case, we could solve for like worst case sample size, which would be like the largest one we needed, just to make sure we got what we wanted. Okay, so and so this solving this equation and figuring out what the sample size you need to like guarantee something. And usually you want the range to be like this much so that I'm not like I want things to be accurate, as accurate as possible. If only I had this value, then I could solve everything. I can get my sample size, I could know what I needed. And so the question is, how in the world do I get this value? Like, give me a worst case even. Give me the worst case of this, because that would make this as large as it needs to be. So it's going to depend. Your worst case standard deviation is going to depend on your data set. And so depends on what your data is going to look like. Okay, so for example, if you're working with percentages, you know that your values of things are going to be between 0 and 1. And now we have to think about, all right, if your values are distributed between 0 and 1, what is the worst case of the standard deviation of all those values? It's got to be smaller than 1, I hope you see. Like, if your values are between 0 and 1, your standard deviation can't be 1, because that would mean, like, okay, all the values are 0, but the standard deviation is right here. No, that just means you put the standard deviation right. The standard deviation is 0 at that point, right? It doesn't make sense for the standard deviation to be farther away than the distance of this range. So that would mean that every percentage was 1 away from the mean, but that means that you did the wrong calculation, right? So we can do a simulation, right? We can try to figure out. So we know it can't be this. How big could the standard deviation be? What's the worst case? All right, and let me prove to you that if it's just a bunch of percentages, and maybe that's useful to you, like you're trying to do the percentage of people who are voting, like percentages are important for us. The worst case is going to be 0.5. Let me show that to you. So this is going to depend on your data set, though, to figure out the worst case standard deviation, but this is going to give us a way to solve for the sample size we need to guarantee a bit of accuracy. The standard deviation of a population of ones and zeros, because that's how you calculate percentages. Like, they're voting for this person, they're not voting for this person, is at most 0.5. Let me show that to you. Oh man, how do I want to do this? Here are some interesting things that you don't have to learn or memorize. There's a function called ones that gives you an array of a bunch of ones. Here's an array of 5 ones. And you can get an array of that many zeros by subtracting 1 from that. So here's, 1 minus that. Gives you an array of many zeros. So I think I'd rather just copy and paste this. And I'll tell you what I'm saying, because I don't need you to remember any of this. It's just some weird looking code. So this is what I want right here, if it copies. this is making a bunch of different options and calculating standard deviations. Yeah, I'll get to that in a second. But let me try to explain what I've done here. I'm trying to show you the worst case of standard deviations. So here I am making an array. I'm making a bunch of sample data sets so we can figure out what's the worst case of standard deviation. So I'm making an array of a bunch of ones and zeros, like 0 ones and all zeros, or 1 1 and 9 zeros, 2 ones and 8 zeros. Like I'm making a data set of just a bunch of ones and zeros, because that's how you can, like, if you take the average of that, you've gotten a percentage, right? So that's my population, and I'm calculating the standard deviation of that population of a certain number of ones and zeros, all right? And yeah, if there's 0.1 ones and 10% ones, 90% zeros, the standard deviation is 0.3 of all those values. If there's 20% ones, 80% zeros, the standard deviation is 0.4. If there's 30% of the ones and voting for ones and the rest voting for zeros, 70% zeros, then your standard deviation is this. And you can kind of see that it's getting bigger and bigger and bigger until it hits to 0.5. There's just as many ones as zeros, like nobody knows who they're voting for. Here is kind of, you can kind of fill in the gaps yourself, I hope you can see. Like, all right, 0.5 is where the largest possible standard deviation is going to be. And that's when everybody's voting for just as many ones as just as many zeros, and that's perfect. That's going to be your worst case. All right, that's like everybody, just as many people over here as over here. So your standard deviation is 0.5 away, because the mean is going to be right in the middle of that, right? Boop. And so that's kind of how that would look. And then, all right, if we've got a population of just ones and zeros, we can solve that equation. We can know that, all right, if I want a 95% confidence interval, the range of that, the width of that to be less than 0.01 for my answers, then I know I can solve this equation and be like, square the sample size can be at most, right, this, right? So population standard deviation, I can substitute that with the worst case value, and sometimes it isn't this. Sometimes you have a better information. This is just worst case. You knew nothing at all about your population standard deviation. This is the worst one that it could possibly be for this kind of data set. If there's values of just zeros and ones when you're calculating percentages, and then you could solve for what the sample size needs to be. So it's like, all right, if you want your width to be guaranteed, even if you had the worst possible standard deviation, if nobody knew who they were voting for, just as many for one as for the other, then you need a sample size of at least 40,000. No matter what. That will give you what you need, all right? But usually, you do have a better estimate. Usually you have better estimates of the standard deviation for the population, and you can get a sample, like you maybe already have a sample or something. So usually you don't need 40,000. You can do better. You can get like 1,000 or something. Maybe you've heard. So, but like that's the worst case. And so you could solve for things. These equations give you power. And here's just like a cool story. Maybe you read in a statistics class or in a math class that like if people are trying to figure out, people are trying to poll people, like you're calling people up to figure out the result of an election, and you're trying to like figure out what all the voting Americans are going to think, you only need about 1,000 people. You only need to call up about 1,000 people, and that will give you an answer within 3% error. That's crazy. And so that's because we know more, right? We can use equations, not just this one, fancier equations that give us what we need. And so when you know more about your data set and your population, you don't need 40,000 people. You just need 1,000 sometimes. But that's to constrain the width of your confidence interval. This is now 3% margin of error. So you can be off plus or minus 3% in your answer. Only 1,004 people will give you what you need. So that's kind of neat. And that is all of the things I wanted to say, I think, today. All of these properties have to deal with the average at the end of the day, right? We've explored what the average can offer us. And it gives us some very cool things. The the greatest thing that it does for us is it gives us the central limit theorem. It turns things into a normal distribution. People like mathematicians have studied the normal distribution extensively. We know a lot of cool facts about it. Like we know that plus or minus 2 standard deviations of a normal distribution is 95% of the data. It's very, very neat, and we can solve for some cool things with that. And yeah, I think that's what I wanted to say. Any questions about this chapter? This is chapter 14. Remember to read it. Yeah, let's, if we're good, the last thing I want to do, we've already got project 2 out, but let me release the things that this chapter depends on. So this is a shorter chapter, but lots of cool things to think about. So it gives us access to some new assignments, so Lab 8 and Homework 9. Let's go figure out when those need to be due now. So Lab 8 first, and then Homework 9. That's the proper order, apparently. Let's see when things are due. And we'll find an empty slot for these assignments. It looks like I can do 2 weeks out in the future, so the 22nd for Lab 8 and the 24th. I like my Wednesdays and Friday due dates. Let's do 22nd and 24th. 22nd. And the 24th. April 22nd, April 24th. That should check out. And I think that's all that I wanted to say about chapter 14. Any last questions beyond the recording? All right.